Hi, Iman, how are you?
Hello, good. How are you?
I can't hear you.
Can you hear me now? Hello,
Just give us a second. I don't, but you're able to hear me, isn't it?
I can hear you.
Let me see. Şeyler. Okay, just some information. Obviously, we are going to start in 2 minutes, but you may want to wait maybe additional couple of minutes to make sure that the presenters are going to be online. Um, you can start with the paper IDs, going from the lowest number to the highest number. But if a presenter is not available at the moment, you may want to skip. But then later in the presentation session, you may want to go back and just ask for them to see if they're going to be online at that time.
Sure.
Other than that, do you have any questions for us?
I think we are good. I just want to double check with you that presenters are able to share their screen, right?
Yeah, they should be able to. But if do you know who's the first presenter is? If
Yeah, it's paper
Okay.
ID
I'm here.
one.
I'm here. I'm able to present. No issues.
Okay, so
This is
let's
Shiva, myself.
yeah, let's give a try to see if you're able to share the screen.
Yep, of course, I will do that. Yeah. Are you able to see?
Not yet. Yes,
Yes.
we can now.
Okay,
Okay.
great. All right, any questions to me, Iman?
No, I'm good.
Mhm.
Thank you.
All right. Okay. Again, thank you for your service. We are waiting for your report after the presentation is over. Thank you.
Absolutely. Thank you.
Okay, good luck.
Thank you. Okay, let's get started. Hello, everyone. My name is Iman Bakilinia. I'm the session chair for today's session. This is session 17. We have 9 presentations today. So please make sure that your presentation is going to be wrapped up in 10 minutes, and then we're going to have Q&A. So without further ado, let's start with paper ID 119. Shiva is already shared the screen. Please go ahead.
Yeah, hi. I'm Henry here. Shiva and I, we are the author of this innovation. So, good morning, everyone. And again, so today's the discussion is around the deep learning-based intrusion detection and cybersecurity framework for connected vehicle, the CAN bus network. So, again, this is related to any of the IoT type of devices. We have a lot of devices in the market. This research is focused on how we can protect and do the intrusion detection and cybersecurity for them. So the agenda for today is I'll briefly walk through the problem and motivation, the existing research, our ongoing proposed methodology, and the key results and findings, and finally conclusion and the future work. So, okay, modern vehicles rely heavily, if we see the modern vehicles heavily rely on the CAN bus communication, which is critical for internal communication between the ECUs. However, this system lacks the built-in security features like authentication and encryption, making it vulnerable to cyber attack, which is very crucial currently. So in our work with our research, we propose a deep learning-based intrusion detection system we call as IDS, capable of detecting multiple type of CAN attacks. So in this research, we evaluated three. I mean, we have evaluated multiple, but we're going to focus on three here, which is a deep neural network, IDCNN, and hybrid CNN and BILSTM. So the hybrid model achieved the best performance with over or little bit more than 90% accuracy, capturing both spatial and temporal pattern efficiency. So we will be focusing more on the following slides that Shiva will share. Um, okay. All right. So the modern vehicles becoming increasingly intelligent with sensors, ECUs, and automation features. But this also increases the attack surface. So the attackers can exploit the CAN bus vulnerabilities to do many things like trigger the sudden braking, cause unintended acceleration, which can cause accidents and so on, and manipulate the steering and injecting the false messages. The common attack types includes denial of service, and then the fuzzy attacks and the replay attacks and ECU impersonation. Since CAN lacks encryption authentication, the intrusion detection becomes very essential, especially with the growing demand of all the IoT and CAN-based vehicles. That's where the AI-based detection systems comes into play. Next slide. All right. Some of the existing research shows the various approaches to the CAN intrusion detection. Some of the methods uses the machine learning models, the lightweight classifiers, and knowledge graphs. While many achieve the good accuracy, they all have come up with their own limitations, like poor temporal modeling and lack of the real-time capabilities. Most of them are near real-time or non-real-time, and then the scalability issues. For example, some models focuses only on the static features, while some do not handle the complex attack patterns. This highlights the need for the robust and the dedicated deep learning model that captures both spatial and temporal behavior. Yeah, I think with that, I think I'll hand it over to Shiva, who will talk about what methodology that we use and how we came up with the conclusion on this.
Hey, thanks, Henry. Thank you so much. Part of this research effort, we went through the data set. In order to do research, we need the sample data collections. Part of that, this is the overall research methodology which we had. If you see high level, part of the data collections, we have publicly available CAN intrusion detection data set. We got it from OCS lab of Korea University. It's around having 4.2 million CAN frames. It is categorized into attack-free, DOS, denial of service, fuzzy attack, and impression classes. So next is data set, OTDS data set. That's what. Then data pre-processing, which is a cleaning and merging, which will CAN frame includes timestamp, CAN ID, a DLC, and 8 payload bytes with 50,000 samples selected per class to create a balanced data set and reliable model training. So the feature engineering, which is a statistical and temporal and CAN ID based on play-based features which is extracted to improve the discrimination between normal and malicious CAN traffic, controller area network basically. So label encoding, which is the next one, label encoding, which is attack categories were converted into numerical labels using label encoder to enable supervised multi-class deep learning. So real-time canvas cybersecurity framework, which can be a result. Otherwise, the feature scaling, and this one is data split between training model we are using 80% and test is 20%. Data set we split it. Implement deep learning models we have, which is 3 models as we mentioned. Deep neural network and also conventional neural network and hybrid CNN by LSTM model and model training and with the hyperparameter tuning, which is after the model evaluation in terms of accuracy, loss, and precision, recall and F1 score. Overall, real-time canvas cybersecurity framework, which is resulted and okay, that's again, it's the same thing. Data splitting, which is, as I mentioned, 80% and 20% testing and 10% of training set result for validation of reducing overfitting. And feature scaling, standard scaler applied around centering them around 0 with unit variance, improving model stability and convergence. Proposed deep learning models, which is DNN, as mentioned, DNN and CNN pattern extraction and hybrid CNN by system. Next is what is the DNN architecture? DNN models consist of multiple fully connected layers with RLU activation, batch normalization, dropout training using ADAM optimization, category across entropy loss, effectively classify CNN intrusion across 4 attack categories, which is part of that. Conventional neural network architecture is the CNN model implies stack 1D conventional and max pooling layers to automatically learn hierarchical spatial features. It can data followed by dense layers and softmax classifier to achieve the robust intrusion detection performance. So a hybrid one, which is seen by an architecture, which is integrates a conventional layer for a spatial feature extraction with a bidirectional LSTM layer to model temporal dependencies. It can message sequences, significantly improving attack recognition accuracy while reducing the overfitting, early stopping and adapting learning rates. So overall evaluation matrix model performance was evaluated using accuracy, precision, recall, and F1 score, ROC, AOC, and confusion matrices, providing a comprehensive assessment of classification correctness, which class discrimination capability and reliability detecting CAN bus cyber attacks. These are the results. As Andreas mentioned in the introduction, we are as part of 3 model. If you see compared to DNN and CNN, accuracy was 90.18, which is CAN system provides. Precision provides 19.819 compared to DNN and CNN. And the recall compared to DNN and CNN, it provides 90.18. F1 score also 90.17. If you see the diagram, if you see the curve comparing DNN and CNN hybrid relation model for intrusion detection. So this one, as mentioned, is a consistently higher precision compared to recall precision and also F1 score. Okay. This ROC curve confirming strong class discrimination with AUC values.
1 minute, sir.
Yeah.
Done.
Okay. Next is real-time detection analytics from the proposed CAN bus cybersecurity framework as models, a comparison between the proposed model and CAN bus intrusion detection. If you see here, proposed model DNN, CNN, CAN system, accuracy point of view, it is 90.18, the accuracy as mentioned, and 19.9, which is compared to 27 and 28 references. This is overall our accuracy point of view 19.18 and 19.17 F1 score, and demonstrating superiority over prior approaches compared to his diagrams. Okay. Conclusion and future work. This study, what we did is a deep learning based multi-class intrusion detection framework, CAN bus networks and presents systematic comparison compared to DNN, CNN, and hybrid CAN system architecture. The experiment result shows hybrid CAN by LSTM model achieves superior performance by effectively capturing both spatial payload features and temporal dependencies in control area network traffic. Rather than focusing on deployment readiness, work contributes structured architectural analysis and unified framework evaluating deep learning CAN bus cybersecurity solution. Future work, what we are planning a future study will evaluate proposed framework on imbalanced and real world CAN traffic dataset, which includes the adversarial and evasion based attack scenarios. And also further investigation will focus on robust and real world operational constraints such as latency, scalability, statistical validation, and performance improvements. With that, there are some references we referred actually part of this, and these are the reference. We can go through our paper, white paper, the research paper. So you will have more details about what and all we captured. Oral details.
Thank you. Thank you. Questions? Any questions? Okay, I have a quick question. So regarding the attacks that you targeted in your data set, I think you mentioned denial of service was one of them. Did your model capture other types of attack too?
As I mentioned, we mentioned, right, phishing, fuzzy one.
Fuzzy attack, a impersonation attack, and then replay attack, and even
Correct.
any anomalies also we will be able to compare from the normal traffic data.
Okay, thank you. And also regarding the data set, you mentioned that you got it from Korean University, if I'm not wrong. Is it something public or no? You had to make a
No,
request.
that is public. So we did some research internally with the data that we already have, but we cannot publicly put it in the research. But we, for the purpose of the research, we use this Korean data, which is publicly available data.
Okay, thank you very much.
You're welcome.
So
Thank you.
let's move on to the next paper, paper ID 139. Okay, it's the presenter.
Thank you.
Sure. Would you please share your screen? Abidus is here, right? Yes, we have your screen, but you're muted, so make sure to unmute yourself first.
Yeah, hi. Am I audible now?
Yes.
Okay. Thank you for letting us give a chance to present our paper. Our paper is titled Improved Prostate Zonal Segmentation Addressing the Peripheral Zone Challenge by a Peripheral Centric Swing Unit. So let's get started. So let's talk about the inspiration and goal. We know that prostate cancer is the second most common cancer in men worldwide. Making accurate segmentation is critically important for clinical practice. Precise zonal segmentation directly impacts cancer detection and risk assessment, treatment planning, biopsy guidance, PSA density, etc. The core challenge we tackled is segmenting two distinct zones, the transition zone and the peripheral zone. The transition zone is particularly difficult because it occupies only 5 to 10% of the prostate volume. It has an irregular shape and shows very low contrast against surrounding tissues. The peripheral zone presents its own challenges because it's the primary site of cancer detection, making accurate segmentation clinically critical. So recent studies have struggled to exceed 80% die score specifically for the peripheral zone. It remains one of the hardest open challenges in prostate segmentation. Our goal was to directly address the gap by achieving greater than 80% for both zones with balanced performances across transition and peripheral zone. While also we wanted to produce clinically accurate volume measurement that physicians can actually trust and use in practice. So we will walk you through the inspiration dataset. We'll talk about data preprocessing, loss functions, and then at last we'll show some of our results and end with a conclusion. So let's talk about the dataset. For our experiments, we use the Task05 prostate dataset from the Medical Segmentation Decathlon, one of the most widely used benchmarks in medical image segmentation research. It's although a small dataset, that dataset consists of 3D multi-parameter MRI scans of the prostate provided by NIFTI format. In total of it has 48 cases, 32 used for training and 16 reserved for testing. What makes the dataset particularly valuable for our work is that it provides manual expert annotation for both prostate zones we care about, the peripheral zone and the transition zone. So before feeding data into our model, we applied carefully designed 6 steps of like pre-processing and augmentation pipeline. First, we did slice filtering. We removed slices with poor or extreme peripheral transition content, ensuring the model only trains on informative and balanced examples. Secondly, we did center cropping. We cropped the image around the prostate region, centering in the frame the removal irrelevant like background informations so that the model only focus on the prostate itself. And third, we did normalization. We clipped intensity value between first to 99th percentile, scale them to range of 0 to 1. Fourth, like slice selection, we kept central slices that are rich in both zones, particularly peripheral content, since those slices carry the most clinically relevant information. Fifth, we do resizing. We upscaled images to 190 by 190 and then downsample to 96 by 96. These two steps resizing helps preserve spatial details during the scaling process. And sixth, we did augmentation. We tripled our training data by applying random flips, rotation, brightness adjustment, and noise. So we did like it became 96 samples. This improves the model's ability to generalize to unseen cases. And for our loss function, we used BCE dice loss, a combination of cross entropy and dice loss weighted equally at 50-50. Within the dice component, we prioritize the peripheral zone by giving it a little more weight by 4 by 6 weight compared to 2 by 6 for the transition zone slice in peripheral because it's the harder and clinically more critical structure to segment. And we also used deep supervision where two auxiliary outputs contribute additional loss signals during training at 30% and 20% weight respectively. The model was trained using the Adam optimizer with a learning rate of 0.0005 with reduced LRO and plateau, automatically reducing the rate when performance plateaus or changes. And this is our architectural diagram. This diagram shows our complete pipeline from raw MRI input to final segmentation output. On the left, the input is an FTI medical image that goes through pre-processing, extracting the 2D middle slice, filtering harmful slices, and applying weighted sampling. We then perform ROI extraction by detecting the prostate boundary boxes, applying a 30% margin, and verifying no pixel loss. Finally, 96 by 96 patches are extracted with 50% overlap, focusing on the peripheral zone with 3 times augmentation. In the center is our actual swing unit model. The encoder progressively downsamples using swing transformer blocks with window and shifted attention, merging patches and like features at each stage. At the bottleneck, a swing transformer block with 8-head self-attention captures global context at the deepest supervision of 512 channels. The decoder then mirrors the encoder, expanding patches back up through skip connection, then preserve final spatial details from the encoder. On the right, the model output 3 classes, background, transition, and peripheral zone, where we are only interested in peripheral and transition. Training uses the Adam optimizer and BC plus dice loss was used with 5 times weight for peripheral zone and deep supervision. So this is the score that we got. We got a good score in both transition and peripheral zone, 94% for transition and 82% for peripheral zone. And here we can see some of our segmentation results. It almost closely resembles the original ground truth. We can see it has captured good for both the transition and peripheral zone. And here we also applied attention heat map to understand whether our model is focusing where our model needs to. So it is focusing at the middle at the prostate region. It is not focusing on any background or unnecessary information, making it a good focus. And then we did volume calibration. See, in clinical practice, accurate volume measurements are just as important as segmenting like boundaries. Physicians use prostate zone volumes to calculate PSA density, plan biopsies, and monitor disease progression. Even a model with good dice scores can still produce systematically biased volume estimation. So we were interested in doing a volume calibration here. Looking at our bland Altman plots before calibration, the peripheral had a mean volume difference of negative 112.7 pixels, meaning the model was constantly and significantly underestimating the peripheral volume, rated as poor. After calibration, the bias dropped to just 20 pixels, rated as excellent. The transition was good. It created 13.1 pixel before, so it remains stable after. Critically, the volume correlation did not come at the cost of segmentation quality. Peripheral dice stayed essentially the same, 0.731 to 711, and transitions dice actually marginally improved from 0.928 to 0.930. Volume calibration also remained solid. So in summary, our calibration successfully correlated a significant clinical bias in peripheral volume estimation within fully preserving the segmentation quality. Uh, so to conclude, we developed a swing unit model with attention mechanism for automatic prostate zone segmentation from MRI scans. Our model achieved good balanced dice scores for both the transition and peripheral zone, addressing the challenge that has held back previous methods. The attention layers learn to focus on automatically meaningful regions rather than arbitrary attending to the image, which gives us confidence that the model is learning genuinely and getting clinical structures rather than shortcuts. And perhaps most importantly, from a clinical standpoint, accurate peripheral zone segmentation directly supports better diagnosis decisions. Since the vast majority of prostate cancers originate in the peripheral zone, so it was important for us to get a good score on that also. A model that segment it accurately is a model that can genuinely assist clinicians in detecting cancer earlier and more reliably. So yeah, that was pretty much our presentation. Thank you.
Thank you. Thank you very much. Any questions? Okay, I have a question. So regarding the pre-processing that you mentioned, I'm curious, did you do this step manually or did you use some automatic tools to perform such tasks?
So it's both. We did manual augmentation and did use some tools as well. So in combination of both.
Combination. And how many images for your data set you used for this model?
So it was 36 and we did augmentation 32. So we did augmentation and made it like 96 by random flipping, rotation and everything because it's a small data set.
Okay, thank you very much. I appreciate it. Let's move on to the next paper. Paper ID 140, Vision Transformers. So, Abdus, please stop sharing so the new presenter can. Yes, we have your screen now, but you are muted. Masum, yes, please go ahead.
Hi, thank you. So our paper title is Vision Transformer for Epilepsy Seizure Prediction and Detection. I am presenting on behalf of my teammate. So I am MD Masum Rana. Abidas, could you please stop sharing your screen?
Oh, sorry. Give me a moment. Yeah. Has it stopped?
Yeah.
Okay.
Thank you. So around 50, according to the World Health Organization, around 50 million people worldwide affecting epilepsy each year. So it's characterized by recurrent seizure, which can be significantly impact patient quality of life. Like electroencephalogram data is used for epilepsy seizure detection, and like we need to better prediction system for patient quality of life, and early detection and prediction of epilepsy can do this. Oh, my PC is just frozen.
So, Masum, if you need more time, what do you think? We go to the next paper and then you can.
Hi. I can share on behalf of him.
Sure, yep.
Yeah.
Yeah, you can share. Yeah, could you please go to the third slide? Yeah. So our main motivation is like traditional machine learning or deep learning model like CNN and RNN have like widely used for the epilepsy seizure prediction, but yeah, here. So there are still limitation capturing complex pattern for the electroencephalogram data. So like need to better accuracy for the real-time detection and prediction of epilepsy prediction, and like there need more advanced model like vision transformer that can be capture spatial and temporal feature. Next slide, please. So this is actually the vision transformer architecture. Like basically, vision transformer is a deep learning model that originally used for the image classification instead of processing the entire image once. So vision transformer basically divides the images into smaller patches. Then it uses for the same self-attention mechanism to understand better relationship between these patches. And we have seen that a vision transformer do strong performance for these patches and for the entire images. Next slide, please. So the vision transformer architecture, like there are several components of the vision transformer. The main component of vision transformer is patch extraction, linear projection, position embedding, transformer encoder, and classification head. So like as I told earlier, it took the images as input as image patches. Then these patches are flattened and projected into image embedding. After that, transformer encoder uses for the self-attention mechanism to extract features flowed by classification head. Yeah, next slide. So here are the examples of the image patches, how the vision transformer take input as an entire image into a image patches. So for example, if we take an image of size 24 to 22 24 divided by 16 by 16 patches, we got total 119 6 patches. These patches are used for like classification or CLS token for the transformer. Then these patches are embedded into like feature spaces. Then it go through the self-attention mechanism. Then finally we got the entire output, whether it's like, take for example, it's the image is dog or image is cat, kind of this. So then next slide, please. So our objective is like main objective is study the recent research on the vision transformer, what other researchers are doing research on the based on the vision transformer and epilepsy and took the electroencephalogram or EEG data. So we analyzed different we collected or reviewed different methods and different data set or like how each researcher or each study use performance metric for their methodology or for their research. We identified like key strength of vision transformer, limitation, or like some future work direction, like how we can improve vision transformer tasks if we include some features on existing vision transformer. So next slide, please. So yeah, prior research is like recent study shows that transformer-based model outperform traditional CNN and RNN model, but some model achieves like accuracy above 98%. Also like hybrid model combining CNN and transformer got better performance or better accuracy. Yeah, literature review, like as I told, in literature, we found that different approaches like attention mechanism, also convolutional transformer improve performance. Many researchers have shown transformer-based approaches can like do entire image into a small spatial pattern in EEG signal, which is very accurate for the seizure detection. And like combining with convolutional neural network and transformer got a better accuracy and other evaluation metrics. Next slide, please. Yeah, lots of researcher or most of the researcher used the common data set, which are Children's Hospital Boston's data set, University of Hamburg data set, or sleepwalk epilepsy center data sets. There are also some researcher use UPenn data set, and some of the researcher use Mayo Clinic data sets for their research. And all of these data set are based on EEG signal, and they do train and evaluate for their model. Next slide, please. Yeah, most of the researchers use their methodologies or their research in accuracy, precision, sensitivity, and for their evaluate their model performance. Next slide, please. So yeah, main outcome, lots of the researchers got accuracy around 99% and sensitivity up to 99.8%. We found that the best vision transformer based model is transformer and CNN, which is hybrid transformer CNN. And top result we found in other research that is channel fusion plus CNN, which is around 99 sensitivity and specificity, and the dataset mostly use CHB MIT dataset, which is Children Hospital Boston and MIT dataset. Next slide, please. We find that vision transformer do well in electroencephalogram analysis. These are especially effective when we do combine in CNNs and vision transformer. Overall, they provide good performance in classification performance. And vision transformer are also able to capture long-range dependencies in EEG signal, which improve the detection accuracy. Next slide. Yeah, we found some limitation of existing research on vision transformer. These include like they are not the existing dataset are smaller, so they are not available large dataset. So we need for better accuracy or like for the clinical trial, we need to do better. We need to large dataset for the real-time implementation. Next slide. Future arc, we suggest using transformer and data augmentation. If we use this feature in the existing vision transformer, then we will get a better result and better accuracy, and eventually we can apply vision transformer in real-time clinical settings. Another important direction, like developing a efficient transformer model that can be deployed in clinical settings. The next slide, please. In conclusion, vision transformer is a promising approach for epilepsy detection. They can improve accuracy and potentially enhance patient outcome. However, most research need to real-time, real-world deployment. So if we can deploy in real-time clinical settings, then like it would be great, or it will improve the patient quality of life, and the prediction accuracy and other accuracy we can eventually know.
Okay.
Thank you.
Thank you very much. Any questions? Okay, just a quick question. So regarding the hardware requirements for having vision transformers implemented, can you elaborate more? What is the requirement? What hardware is required for running such models?
So I think as we don't have the large data set, we have the small data set on electroencephalogram data. I think we can run this model in a normal PC, but if we get the large data set, then maybe we need the more tensor or like concurrent PC or concurrent NVIDIA hardware. Other than, I think, as the dataset are like CHB MIT's dataset is smaller. Also, UPenn dataset, Mayo Clinic dataset is smaller. So yeah, we can easily run this dataset on our current PC or current hardware. But when we'll get the large dataset, then maybe we need the supercomputer or like NVIDIA's hardware.
Okay, thank you very much. Thank you very much.
Thank you
I
so much.
appreciate. Sure. So let's move on to the next paper ID 211. Samuel Alam, if he is available. Yes, Samuel, please share. Yes, please go ahead.
Can you see my screen?
Yes.
All right, sounds good. You can see my screen, right?
We can see your screen, but we also can see your notes. So if you want
Notes
to
as
just
well.
share your screen, then you
Okay.
probably should choose the other.
Okay, then give me a second.
Yes, we can see your screen.
Can you still see my notes?
We can see your screen. Please continue.
Yeah, but can you see my notes as you said earlier?
Yes, notes of the slides are also there, but it's okay.
Okay. All right. I'll start then. Hello, everyone, and thank you for this opportunity. Today, I'll be presenting the paper Info10 PC, exploring the privacy concerns within in-vehicle infotainment data services using TAM. I'm Samil Alam. Will be presenting throughout this presentation. So in the table of contents, this is what I'm going to go throughout the presentation. I'll be introducing the paper, talk about some of the literature review that we found, the research model, and the hypothesis development, then the methodology to develop the hypothesis, and the implications after that, and some of the limitations and future work that we found, and then conclude the presentation. So the autonomous and intelligent connected vehicles always provide us with some sort of convenience services such as traffic, real-time data navigation. Where we have personalized audio video recommendations, other sorts of assistance and driving assistance that they offer, which actually gives us a lot of accessibility to collect information and share information throughout the V2V or V2 everything, which is vehicle to vehicle and vehicle to everything network system. Sensors and devices help us to collect those information and then give us the ability to reach that kind of services. So in-vehicle infotainment actually require those data to provide those convenience features that I talked earlier. But these transmission of data is always considered some sort of risk. Risk such as it can be treated some other way that we don't know. So organizations usually do not be transparent about those data possession, and this can be due to having these networks coming with the 5G capabilities and many other network technologies that are out there. So this paper actually explores the user trust that provides the user trust behind acquiring this data and providing data to their in-vehicle infotainment system that they already have in their vehicle. And then we try to understand the privacy concerns of users about sharing information using the technology acceptance model, TAM. Throughout our literature, we found that to the right is our table in the paper, and to the left is a summary that we found from the literature, that the perceived security risk and the perceived privacy risk has a negative effect on user trust. That is, these users have that sort of negative impact when they have already perceived knowledge about the risk of sharing data. Users tend to restrain when they see there's sensitive data being shared throughout their IVI. Some of the variables that the literature found is gender, age, race, ethnicity. These also come into factor. The higher perceived privacy risk also reduces the willingness to share those data throughout their in-vehicle systems. And then also perceived usefulness kind of influences user attitude throughout various literature that we have seen. One of the things that we found in the literature is structural equation modeling is a very likely adapted tool or method used for such analysis for perceived privacy concern. And the results from different literature shows that the perceived privacy concern increases perceived privacy risk. Moving on to our research model. So we built this research model based on the technology acceptance model introduced by Davis et al. Back in 1989. We adapted from the TAM2, which was later modified and based upon original TAM, and we took social norm from TAM2. And then from privacy calculus aspect, we have seen that perceived usefulness and perceived ease of use is seen as the benefit construct. That is, it's like a trade-off that the perceived usefulness and perceived ease of use is the benefit factor if we see it through privacy calculus perspective. From a trust TAM perspective, trust is also integrated in our model, as we can see that hypothesis 2 leads to trust in providers on the right-hand side diagram. In the model, we can also see that users perceive benefits, and they are more likely to adopt an IVI system regardless of any privacy concern. So whenever there's a high benefit in an IVI system, user somehow neglects that privacy concerns that are around it. So to slightly talk about these constructs, perceived privacy concern is regarding the collection and processing and potential misuse of personal information throughout infotainment systems. Perceived privacy risk is the likelihood of losing control over your personal data that you provide in your IVI. And then trust in providers is the confidence that a user has towards the infotainment providers that they have in their in-vehicle. Perceived usefulness is the degree to which the infotainment systems are seen as a convenient product, a good driving experience product. Perceived ease of use is the extent to which the users find infotainment systems user-friendly and very interactive and easy to operate. Social norm is the perceived pressure or peer pressure that you have to use the system being in the society. Behavioral intention is the user likelihood of adopting or rejecting the technology based on various influence factors. These are the constructs from TAM, TAM2, and privacy calculus blended together, but seen in the perspective of infotainment systems. So based on this research model, we have developed our hypothesis where we say that PPC, perceived privacy concern, significantly influences perceived privacy risk. That is, when users have some sort of when the users increase the perceived privacy concern, they worry that their in-vehicle data might be exposed inappropriately. In hypothesis 2, PPC negatively influences trust in infotainment providers. That is, the privacy-sensitive users might view infotainment providers, including any automakers, less trustworthy if they're worried about their personal driving data being misused. To support hypothesis 3, which is trust in providers influences perceived privacy risk. So if drivers trust that the infotainment system implements robust privacy and security protocols, they will kind of perceive a lower degree of privacy risk overall. And in hypothesis 4, trust in providers positively influences behavioral intention to use IVI. So if drivers believe that service providers are dependable and will protect their data from any sort of misuse, their intention to adopt those systems will increase. Perceived ease of usefulness positively influences behavioral intention to use infotainment systems. That is, if the system's interface is designed to be very much user-friendly, intuitive, those privacy concerns will kind of be eliminated, and drivers will more likely go over and use that system. Again, perceived use of usefulness positively influences perce- perceived usefulness. That is, a user interface being clear, intuitive, again, reduces error and makes it more acceptable. For hypothesis 7, perceived usefulness positively affects behavioral intention. In scenarios where the benefits of connected services such as real-time navigation, improved comfort, safer driving, these all actually affects those behavioral intentions. So if you get a better scenario in those cases, users adopt the technology.
2
And
minutes.
then finally, hypothesis 8, social norm positively influences behavioral intention to use infotainment system. So if drivers perceive that their IVR service is a widespread practice, everyone uses that. It can be through any sort of peer pressure or social network. They will eventually start using it as well. So the methodology the methodology is to propose a research design. So we propose a research design to collect data from IVR users in order to measure those constructs that we discussed throughout right now. Our target population could be drivers or specifically IVR users. Sampling can be done directly from automotive clubs that can be found throughout social media, or most likely dealership customers would be the best case scenario. A questionnaire structured survey is the best way to collect those data. We influenced to use Likert type scale from point 1 to 7. A pilot test is fully recommended. We recommend a set of 30 people that specifically uses IVR users, so that pilot test gives you a better flow to start. Data collection can be done using various survey tools that we have out there. Finally, a 300 sample should be a very good case in order to start this and floor this design. We think that approximately this research design should take around 16 weeks, can extend to 20 weeks as well.
Samuel, please wrap up.
Okay, all right. The implication that I've been saying is that this is very useful. This data will be very useful, and trust builds along the benefits that it comes through. Some of the limitations that we had is that there is a challenge to establish causality in survey. There's biased judgment in social norms, and during the data collection, people might have some recalling memory, and they might give some bad data as well.
Okay, thank you very much. So in
Thank
order
you.
to save time, let's keep the Q&A offline. If you have any question, please reach out to Samuel. Samuel,
Sure.
please stop sharing.
Thank you.
Let's move on to the next paper ID 222.
Yeah, am I audible?
Mohammed, yes, we can hear you. Please share a screen.
Yeah, can I? Hi, can you guys see my screen?
Yes.
Yeah. Oh, let me. So hi everyone, my name is Muhammad Abdul Muizia. I'm here to present our research database for the readiness and examination readiness. This work has been done under the Department of Applied Computer Science, University of Winnipeg, Canada, under the supervision of Dr. Maria Tadayo. So to start, the authors have no conflict of interest. I will go through the table of contents. I will start with the database forensics, then related work, methodology, experiments, and I will conclude with the future work and some insights. So what is database forensics? Database forensics is a branch of digital forensics that deal with information deals in the database. So the formal definition can be it deals with the information or the process of identifying, preserving, analyzing, and presenting the evidence of a database. So what are the types of database that are being investigated right now? We have SQL and NoSQL databases. SQL databases which are like more structured, which have fixed schemas. Examples would be
Popular example would be MySQL. And then we have NoSQL database, which is schema-free and more distributive and flexible. Examples are Redis and MongoDB. So, what are the unique challenges that we face in the NoSQL systems? Each NoSQL systems has different architectures and logging mechanisms. So now we have different types of NoSQL systems like MongoDB, Cassandra, Redis. So for our case study, we use Redis. So it's used as the cache layer, and MongoDB is used as a main database. So each NoSQL has its own role. So because of that, each architecture can be different from each other. And then we have limited logging. So the main purpose of the NoSQL is to have efficiency, speed. So they often lack metadata logging, because more data means that have pressure on the systems, and that can cause bottlenecks. And then we have complex recovery. Data stored in across distributed nodes increase the complexity. So now NoSQL databases works in a distributed environment, right? So now evidence is distributed in the different areas, so which make difficult for a forensic expert to find or reconstruct the evidence. So what are the related works? So there have been some works done in the past in the NoSQL and database forensics. There is some work that we think is closely related to our work. So paper number one, which works on the idle log setting, that tells what kind of log preferences we should have to have an effective reconstruction and forensic analysis. And then we have paper number two, which review different types of NoSQL databases like MongoDB, Cassandra, and then compares its authentications and logging capabilities. And then we have paper number three. They also analyze Redis as we do, but they basically analyze the persistence evidence like backups and other append-only files logs. And then we have paper number four that use logs for crash recovery and how these logs can be used for forensic forensic analysis. So why are we using Redis, right? It's an in-memory database. It's mostly used as a cache layer. So because of this in-memory architecture, data can be lost unless RDB and its persistence has been enabled. And also the forensics logging and audit capabilities are still limited and still underexplored as compared to other databases like MongoDB and Cassandra. And now, as we go to the system setup, we have Redis in the distributed master replica setup, and then we have two virtual machines to mimic the environment. And then here's the setting of the virtual machines that allows the different virtual machines to connect with each other. And then we have the experiment. We do different CRUD operations for our purposes. So here are the volatile artifact sources. And we can see here, here is the timestamp, here is the IP address and the command and operation. So this monitor command basically gives the output or the operation runs by the user. And then we have ACL, basically tell the username and the client info and other more information about the user and what kind of access does the user have. And then we have config get command, which basically tells the operational environment, what kind of system settings does we have. In this case, we can tell append only file is to yes is enabled. And then we have non-volatile artifacts, which is append only file. Here is the path and the Redis server log. Each have different paths. And then we have Redis config, which basically allow us to do the configuration changes in the Redis environment according to our needs. So here is an example of hexadecimal file. It's open in the hex editor, and you can see we can basically get some evidence from the AOF file, like number of arguments and number of bytes, and we get a whole structure of operation, including command, bytes, and the number of arguments. So basically, it tells the importance of AOF structure and that we can extract some value from the persistent files as well. And then we have the experiment setups. Here are the different user roles: student, teachers, admins, limited permissions for students, then broader access, and then full access. And number of commands have been tested. There are mixed number of commands. So we can go from simple addition to a BG write AOF command that completely write off whole the persistent files. And then we have less critical commands that basically changes the we can say operation or the variables. What kind of scenarios we are being doing. So scenario number one is normal operation. We usually execute a series of critical, less critical commands, and then what we have is a metadata capture, timestamps, command outcomes, and then example could be a teacher using a simple asset command to add a member of a set, and then we have an unauthorized SS attempt. In this case, a student attempt to execute a critical command like flush all. What this command do is basically delete or flushes all the database from the start, and then we check for errors, message, or metadata in the logs. And then we have system maintenance. We basically checks the perform system level operations, and then we have simulated security incident with deliberately execute unauthorized commands like invalid ACL such users. So what kind of analysis did we get from that? So in the terms of user identification, monitor logs lack user specific identification, right? So to track a user, we need a user ID, right? And so incorporating a unique user ID in log entries would significantly improve traceability, accountability, investigation. So what we can suggest is that logging enhancements should focus on authentication modules, integration points, and capturing details such as user tokens or session IDs at connection of time. That will give us a more broader view on what user is doing what kind of operation. In terms of error reporting and session duration, we can see a gap, error, lack detailed reporting, and no session duration data is available. So because of this, detailed error logs could pinpoint vulnerabilities, right? While session data detecting prolonged and sufficient activity, and like unusual session can pinpoint to a vulnerability or a like a way of intruding of a hacker or something like that. And suggestion utilize session management to log connection timestamps and duration and disconnect reasons. So we have till now explored monitor command, which basically tells the live commands and user activity analysis. And then we have persistence files that tells the data persistence, and we can get a whole historical reconstruction of the file. And then we have ACL, basically act as an audit fixture. And then we have config command, basically monitor, gives the operational view of the system. And then we have a snow log, basically tells what kind of operation have been performing too long, which can be a threat or which is unusual as before. And then we have memory snapshot that was not in our scope, but we here the diagram shows that if we combine or give the whole combine all of this evidence, we can get a whole view of digital forensic investigation, like from user activity analysis to operational and the bottlenecks. And what are the conclusion and future what we can get from this is that in digital forensics, isolated evidence really tells the whole reveals the whole context and the intent, and the result indicate that Redis is in default configuration provide only partial forensic support, and Redis default logging capabilities offer basic operation information and provide limited details about unauthorized command execution. So while logs may capture some activity, and that the depth and the granularity required forensic analysis such as user attribution and detail event reconstruction are often lacking. Uh, so what are the potential benefits we can get from digital forensic readiness? Enhanced forensic readiness, the improved logs would facilitate a faster investigation into security incidents, and we can get a proactive monitoring by enriching logs with actionable data. Redis adds proactivity and identify mitigate threats, and then we have increased reliability, which basically strengthens the logging capability and makes good choice for application required for forensic audit trials. So here are the references we use for our work, and thank you for listening. Yeah.
Thank you very much. I appreciate it. Are there any questions? Okay, just quick question. So does Redis have an option that you can set the level of logs to be? Mhm.
Yep, we have it. In the Redis server log, we can change different settings to verbose, to notice, and different kind of operation. We can do it by going to the config file and change according to our needs. But the problem is that by default, we have different type of server. If we do like a more robust or a more verbose settings, it may affect our system. Like more information will cause more bottlenecks and slow our system. It depends on our needs, what the person wants.
Okay, thank you very much. I appreciate it. Let's move on to the next paper, paper ID 374. Karthik, are you here?
Yes, I'm here.
Yes, please go ahead and share your screen.
Can you see my screen?
Yes.
Okay. Good afternoon, everyone. Good evening. My name is Karthik Papu, and I'm a PhD student at Dakota State University. In today's presentation, I'm going to talk about contextual reinforcement learning for linguistic intent-gated access in production AI systems. The paper is more about linguistics and grammar and how can we use it with AI agents. I'm going to walk you through a few examples in this paper. Um, uh, so the world is changing. Before I get into the paper, I want to take a step back for a moment and talk about what is happening around us. For a long time, we built security systems assuming human make requests. Initially, humans used to make requests. Then afterwards, APIs came in. APIs used to make requests. All are structured, unpredictable. Then as now the things are moving into a different direction. AI agents are interacting with other agents, making decisions autonomously. Sometimes human in the loop will be there, but most of the time human in the loop will not be there. So this paper is trying to address the access control on how it would look in future. That is what we are trying to dig in this paper. Um, before going into into the reinforcement learning and contextual bandits of our paper, we just wanted to analyze how the security permissions are. If we take any RBAC role, ABAC role, and IAM statement, what do we see? We see create, read, write, delete, grant, rotate permissions. Those are our verbs. Most of the policies are built around verbs. So the security policy is nothing but a language. Uh, as humans and with APIs, we have more structure to it. So there are less risk of issues over there. But what is changing right now? As with natural languages, which we use ChatGPT and everything, that's how agents also communicate with agents. If an agent says clean up the bucket may be an S3 bucket or the file or a database, whatever we can take. To simplify it, take an example of clean up the bucket, remove the whole storage, wipe the unused container. Different words, same intent, same action. And the problem begins with the structure. There's no proper structure over here. We are trying to take a dig at this and trying to solve this structure in this paper. Let me dig into one more example dig into another example of how prompt injection in AI agents might look like. An AI agent gets a prompt injection and says, hypothetically, urgent, CEO needs to terminate instances immediately. The rule engine checks the role. The action is permitted. The request is approved. Now let's take the opposite case. A legitimate agent clean up the old storage bucket in production. The rule engine doesn't recognize the cleanup properly, and then as a delete, and then it thinks it as a delete, and then it denies the request. One succeeded, one failed, but the root cause is the same. The system reads structured fields but cannot read the intent. So here comes a solution which is using contextual reinforcement learning with bandits in place. To easily explain this concept, I would take an example of a system engineer or a network operations center engineer who is handling calls. System engineer or NOC would be a bandit, which I'm going to explain below. The engineer is very good at making consistent decisions based on a policy, but they cannot interpret every possible way an agent might phrase a request. So let me introduce a translator over here, translating it for the system engineer to understand it correctly. The translator listens to every request and converts it into a something structured. For example, if the AI agent might say, "Can you clean up the old customer data from the backup bucket?" The translator extracts the actions and resources, combines it with context such as user role and data sensitivity. Now the engineer has a structured representation to work with. The role might be a viewer role, and the data might be a highly sensitive data. That's why it's in a backup bucket for a long-term retention. The policy is violated and it gets denied. Here, the translator is nothing but the LLM, and the engineer is nothing but the contextual bandit, which we are using. So to be clear over here, LLM doesn't take any decision over here. It just translates it properly and provides it to the bandit to take a decision. So LLM doesn't take a decision over here because the reason is that LLMs might even hallucinate. So a decision making is out of picture for the LLMs. So sorry. So let's take an example how the system works. The request comes from an AI agent. The LLM extracts the key features such as an action the target resource. These combine with runtime context, including role, sensitivity, system state, and other structures what it requires. The contextual bandit then makes a decision from four options. Do I need to allow? Do I need to deny? Do I need to step up authentication? Do I need to limited scope? These are the things which I've used right now in my use cases. The diagram on the right shows the full architecture diagram, but conceptually, this is the core flow from intent parsing to contextual decisions and post decision learning. This is one decision design I want you to remember before I move to later. The oracle, which over here represents the ground truth. It is used for post-decision rewarding during training and evaluation. So everyone requires a reward, right? If you are rewarded well, you do work well. So here in this case, we will be rewarding the system well if it performs well. So, regarding our evaluation, this is a synthetic simulator. We have used Open Gymnasium by OpenAI. OpenAI outsourced the Gymnasium tool, in which you can create multiple gym environments for multiple scenarios. In this case, we used the scenario for creating a synthetic simulator for identity access management. What we used over here is we use many type of categories of verbs, which are delete, grant, rotate. We have used around 8 verbs and 10 resource objects. Resource objects might be storage buckets, IAM keys, Kubernetes containers, BigQuery tables. We have used multiple of those things. What we did over here was totally we have around 8,000 odd unique requests with a total episodes of 270K, around 270K episodes. Episodes is nothing but each and every episode is nothing but create go ahead and delete the container or like that, which is more aligned towards the production logs. How we look at the production logs, those each and every episode look like the production logs. So on the top of it, we have added even jailbreaking attempts, social engineering requests, like I have shown in one of the slides where the CEO wants to delete the instances, memory injection, and privilege confusion. So we took some of the things from the MITRE ATT&CK framework also of few of the privilege escalations, and we tried to add it to this one. So, we'll come to the results as we are running out of time. I want to be quick over here. We'll come to the results. The results are we found it to be that the contextual bandits have an accuracy of 99.5% on unsafe approvals. ABAC, which is one of the industry standards. ABAC is used less, but RBAC and AirBAC, I just mentioning ABAC over here, reduces this to about 5.6%, 5.46%, what we have seen fit unsafe approvals. But Linux, LIN UCB, which is our contextual bandit, drops it down to 0.10%. This is even before the Linus UCB doesn't have pre-training data. Without even pre-training data, it was able to understand. LLM was able to properly give the context And then we were able to, the contextual bandit was able to do the same thing. When we did aberration testing under stress, we found that the RBAC, ABAC, and all the standard ones, the false, the unsafe approvals increased from 5.2 to 24.4%. The Linux UCB maintained almost around 0.10%. So, Linus UCB with the contextual bandit was able to take proper decisions even under attack. To repeat again, we trained around with around six verbs. So we like forecasting what we do. We did train around only six verbs out of the eight verbs what we had. We then tested the unseen verbs, which is grant, control, and rotate key, which even the RL didn't knew about it. Even at that particular point, we were able to have good performance with our RL system. The natural extension to this one is to this paper is if we get proper resources in future, we are going to implement it in production system. Here, with the knowledge which I have as a cloud security engineer, as a PhD student, I was able to get the episodes almost correctly, but deploying it in production will provide us accurate results. Repeating the same thing, things are changing. Agents will be communicating with each other. So we need to have language in place, linguistic gated controls in place in order to secure our assets in future. Thank you. Please let me know if you have any questions.
Okay, thank you very much. Are there any questions? Okay, just a quick question. So
Yeah.
regarding the code that you shared on your GitHub repo, can you just elaborate on it? What is basically
So
doing?
I'll be uploading the code after the presentation. So it's basically for every paper. This is a paper series of papers I am writing. No, this is one of the paper which on concentrating on language. Previous papers were on AI agent authentication authorization. This one uses Gymnasium as a background of OpenAI. I created a gym which simulates all the episodes. I call it as episodes of what happens in a production AI production cloud environments. So it simulates it and then uses different type of parameters like adding stress to it and all those things. ABAC was implemented easily in production systems. It's quite hard to implement ABAC because you need to have ground up governance. But here, as it's a simulated environment, I was able to even simulate ABAC properly. So the code is structured. After this, by the end of the day, I'll be uploading the code.
Okay.
Just because I wanted to make sure my work is protected, I wanted to
Right.
have the code uploaded at the end of the session.
Okay, thank you. Thank you very much.
Thank you.
Let's move on to the next paper. Paper ID 386.
Hello. Just wanted to confirm if you're able to see my screen.
Yes.
Okay, perfect. All right. Hello, everybody. My name is Pragya Bhandari. I am a PhD candidate at the University of Maryland, Baltimore County. And today I'm presenting my research, which is actually a part of my research, titled Temporal Behavior Archetypes of Ransomware in Active Directory Environments. A little bit about what to expect in this talk. I will be starting with significant findings and then talk about why I began this research, some past works, how I did it, and some results before we concluded with conclusion and future work. So some significant findings from this research was that we introduce a temporal alignment and density-based clustering framework for analyzing ransomware behavior in enterprise environments. This framework combines dynamic time warping for temporal alignment with HDB scan clustering to identify recurring behavioral structures in Windows event logs, which we'll talk about further. Second, our analysis provides empirical evidence that ransomware behavior in Active Directory environments converge into shared execution patterns rather than forming strictly separable family-specific behaviors. And finally, this work introduces a data set called RIAD, ransomware and Active Directory environments, which will contain all the Windows event logs that was collected from my experimental analysis. So let's get started with the motivation. We know that ransomware has been violating a lot of SLAs and a peace of mind from early 2000s. But although there are malware data sets available like Sorel, Ember, and a few more to name, there is no publicly available ransomware specific data sets as such, and no data set that would target an enterprise environment. Another motivation was that the traditional detection lies on file hashes, static signatures, and family specific indicators. But these approaches do fail against new variants and polymorphic malware. This is an issue that a lot of researchers have been facing and something that we've been researching for. So the specific question that I have focused on in this research is, do ransomware families actually produce distinct behavioral patterns in Active Directory logs, or do their execution behaviors converge in enterprise environments? The related work could find prior research work that's related to this, but not exactly what has been done in this research. Like the first category of Active Directory security and attack monitoring, there were some previous work that focused more on attack techniques like credential dumping or lateral movement within the AD systems, but no talk about any machine learning techniques worked on. So if you look at research that talk about ransomware and machine learning, then there were a lot of research that worked in this intersection, including one of my prior work. There's also an approach called Ranker that used host-based behavioral detection systems, which analyzed system activity on individual machines to detect ransomware in execution. As far as the temporal sequence alignment that I have been using, there have been prior work, possibly in the field of malware analysis, but not exactly related to ransomware, or these techniques have not been used to work on the question that I have focused on in this research work. So hence the limitations for all the previous work is that all of these studies focus on a single machine, post-infection behavior, or a non-Active Directory telemetry. They also don't really produce a data set as such. So now talking about the methodology we've used, this was borrowed from one of my previous work or my PhD research, where I have created my own environment since we don't have any publicly available ransomware data sets. I created this environment in a Proxmox sandbox. I have 3 machines, one server, Windows Server machine, and 2 Windows client machine, as depicted in this image on the right. One of the client machines, the machine on the right, is my victim machine. Now, in this victim machine, I have all of my ransomware binaries. I arm my ransomware binaries and then I run the ransomware samples onto that machine. I wait for about 20 minutes because I want to focus on the first few minutes of the ransomware attack. And then after 20 minutes, I collect the data as is from Windows event logs from the victim machine and the server machine. And then I transfer all of that data into the second client machine and to my local folder. Now, this 2-step approach was necessary to make sure that the ransomware does not escape this controlled environment. When I said I collected the Windows event logs, I've collected 3 types of log files: security, system, and application. All of these data was then filtered out for the first only 20 minutes of the execution, and that becomes my data set, RIAD. Now, I was answering a lot of research questions based on this entire experiment that I've done. The core of this entire experiment was to understand the behavior of ransomware. In order to do that, of course, I have my raw logs. Now, this methodology or this paper captures the 5-step approach that I've used in order to answer my question. It starts with representing the event logs as sequences. To be more specific, each entry is converted into a token. And that token format looks something like the example that's shown on the left. We have an event ID. We also specify the machine type, which could be of two types, which is a server or the victim. And then the log type, which is one of the three files, which is security, application, or system. Once we have combined these three attributes to create a discrete token, we then use these tokens to construct a multivariate time series matrix where rows represent time bins and columns will represent event tokens. So this representation will allow us to model ransomware behavior as temporal sequences of system activity. After we have these event logs as sequences, we try to capture the execution dynamics. To do this, we divide each ransomware execution run into fixed time bins of 2 minutes. For each bin, we count how many times each event has occurred, and this allows us to measure how different types of system activity appear and change over time during execution. So the result is a multivariate time series where each time step captures the intensity of different event types. The next step is instead of analyzing the entire execution run as a single sequence of 20 minutes, we focus on localized phases of the activity. So to do this, we extract overlapping sliding windows from the time series data. So each window spans 10 minutes, and we move the window forward with a stride of 2 minutes. For example, the first window captures activity from 0 to 10 minutes. The next window will capture from 2 to 12, and so on. So this approach allows us to capture different stages of ransomware execution, such as early bursts of activity or delayed escalation. Once we've done with that, we try to compare the ransomware execution with each other, each one of those windows. But one of the major challenges in this case is that their behaviors are not perfectly synchronized in time. As I've noted, I have run at least about 120 samples of ransomware of 9 families each. 9 families. And what I've noticed is that one ransomware family might perform, let's say, a privilege escalation at minute 4, while another performs the same action at minute 6. So if we compare the sequences directly, these small timing differences can make similar behaviors appear very different. So to address this, we use dynamic time warping, which aligns the sequences even when events occur at slightly different times. So this allows us to compare behavioral windows in a way that is robust to temporal shifts in activity. And the last part is the clustering technique that we've used. Once we have computed the similarity between behavioral windows using DTW, HDB scan, which is hierarchical density-based clustering was applied. HDB scan will group together windows that exhibit similar temporal behavior while separating windows that do not belong to any clear group. One of the major advantage of HDB scan is also that we do not need to specify the number of clusters in advance, and it does not need any labels. This algorithm is also robust to noise and outliers, which is good. In our case, the input to the algorithm is the DTW distance matrix between all behavioral windows. And the output we are expecting is a set of clusters of temporarily similar behavioral windows, which we could interpret as recurring ransomware execution patterns. Now, let's visualize this clustering structure by projecting the behavioral windows into 2 dimensions using UMaps. Now, this UMap is basically a projection of the DTW similarity space in 2 dimensions. Each point in this plot represents a temporal window extracted from ransomware execution run. Windows that exhibit similar temporal behavior appear closer together, while different behavioral patterns appear farther apart. Even without labeling, we can see that the windows naturally organize into groups, which suggests the presence of recurring execution patterns across the dataset. Here I've highlighted several of the groups that emerge in the embedding. These clusters represent sets of behavioral windows with very similar temporal activity patterns. The HDB scan identifies these dense regions in DTW similarity space and groups them together automatically. In total, the algorithm identified 4 non-noise clusters, which we will interpret as recurring behavioral archetype. I have highlighted 3 of these. The 4th one is one among the larger group of clusters that we can see on the left of the image. So let's look at the table results for understanding it even better. On the left, we have the window level clustering captures, which captures local behavioral patterns. And on the right, we have run level clustering, which reveals overall execution pattern. So in the window level on the left, the table that we have on the left, each data point represents a short segment of ransomware activity. This could be the bins that we have calculated in. Clustering at the window level helps identify recurring behavioral fragments that appear across different ransomware runs. These clusters reveal common behavioral patterns such as bursts of authentication activity or file operations. The run level, the table on the right, is where each data point represents an entire ransomware execution of that 20 minutes that was run. So instead of short segments, this captures the overall behavioral pattern of the run. As we can observe in this table that in case of window level distribution of archetypes, we see cluster 2 had the most better results. Even in case of run level, we could see that the dominant archetype was the cluster 2 in both of these cases. So let's further look into the graphs that will allow us to interpret these results even better. Each one of the clusters that was formed from HDB scan, we looked at each one of the event IDs and grouped them into behaviors based on the MITRE ATT framework. We basically mapped the raw event tokens into categories such as logon activity, credential use, process creation, service modification, and application activity. So the plot or each plot shows the average temporal activity of these categories across the aligned execution window for one cluster. Looking at these profiles, what we can see is that each cluster represents a different execution dynamic. For example, cluster C2, which dominates the data set as we've seen, shows a pattern of early activity followed by gradual decline, indicating an initial burst of system interaction during execution. Cluster C0 shows a delayed peak, suggesting that certain behaviors occur later in the window. We have cluster 1, which shows moderate early activity with gradual decay, while cluster 3 will capture a short-lived spike pattern with minimal sustained activity. So these patterns illustrate that ransomware executions converge into a small number of recurring temporal archetypes rather than forming a strictly family-specific behavior. To quantify that relationship even further between the ransomware families, the behavioral archetypes we discovered, we performed a run level chi-square test of independence. Each execution run was assigned its dominant archetype, and we examined whether certain families consistently map to a specific archetype. The test produced a chi-square value of 14.84 with a p-value of around 0.062, which indicates that the association is not statistically significant at the conventional 0.05 level. However, the effect size measured by Kramer's V is around 0.318, which suggests a moderate association between family and archetype. So, in practical terms, this means that while some families show slight tendencies towards certain patterns, ransomware behavior in Active Directory environments is strongly separated by family identity. So there's no strong statistical separation, but there is a moderate association. To summarize, our analysis shows that ransomware families are not strongly separable based on early stage activity in Active Directory logs. Instead, ransomware executions tend to converge into a small number of recurring temporal behavioral archetypes, reflecting common operational patterns within enterprise environments. Finally, to support further research in this area, we are releasing the RAD dataset, a reproducible dataset capturing early stage ransomware behavior in uncontrolled Active Directory testbed. These findings suggest that enterprise and ransomware detection may benefit more from modeling shared behavioral patterns rather than family-specific signatures. There are several directions of extending this work. We could scale the data set further. We could also strengthen the features that have been included in my analysis. We could use the other features that's available in the data set. Could also look into the tensor-based temporal representations. If we're talking about temporal representations, it would be more useful to look at more than 3 dimensions. We can also integrate further AD semantics, like look into AD-specific attacks. We could also broaden the framework by adding more client machines. And with that, I would like to conclude my talk. The code and the data set is available on this GitHub link, and this QR code is totally safe. I've tested it. And thank you so much for your time.
Thank you very much. Thank you very much. Are there any questions? Okay, I have a quick question. Have you considered IMP hash or import hash in your research? Does it reveal any relations between the samples that you had?
Yes. So the data set that I was working on only has the event IDs that I have collected, while the hashes, if I might say, if we are talking about import hashes, and I'm guessing that question arises because we are working with malware samples.
Right.
Yes. So malware samples definitely has a lot of static features such as the PE hashes. Now, the malware samples that I've used in my research, you can find the static features of those as well. But this research in particular did not focus on the static. Rather, I worked on a dynamic feature called like the Windows event logs with respect to
Yes.
time.
Very good. Thank you for sharing.
Thank
Yes,
you.
so for import hash, the idea is that what if we find the API request that a malware submits? And since, as you mentioned, the sequence of requests for family of
Yeah.
malware samples probably look similar, maybe there are some similarity in the import hash. Also, I'm not sure if you consider, as you mentioned, this is related to a static testing, but fuzzy hash options like SSD can also sometimes help in terms of finding. Maybe for the future, maybe you can consider comparing the result that you have with those options. Just a suggestion.
No, yes. Thank you for that suggestion for sure. I think if I explore further down to this research, and I would love to collect the API functions as well. As a matter of fact, one of the motivations to do this work was because I was working with static data, like the API handles, the API functions, and one of the things that's missing in our static features is the pattern in which those events occurred. But yes, that's something that could be extended. This work could definitely be extended.
Okay,
Thank you.
thank you very much. Thanks. again. So let's move on to the next paper, paper ID 399.
Hello.
Hello.
Sharing. Let me know once you see it.
Yes, we can see.
Okay. Good afternoon, everyone, and thank you for having me here. I am Usha Ratnam Jamula, and this is joint work with Nagasujita from Cornell University. Today I'm presenting DarkMine, a deep learning framework for dark web threat intelligence for basically dark web communications. The key idea, instead of waiting for attacks to happen, we can mine dark web, forums, marketplaces, and chat channels to identify threat actors, map criminal organizations, and predict attacks before they occur. So let me walk you through how we did this and what we found. The intelligence gap, let me set the stage why this matters. In 2024 alone, ransomware damages exceeded $20 billion, and dark web forums were central to planning many of these attacks. Over 22 billion records from data breaches have been exposed with stolen data regularly but traded on underground markets. The fundamental problem is that current threat intelligence is reactive. Security teams discover attacks after systems are already compromised, and attribution rarely goes beyond broad labels like nation state actor or financially motivated group. Manual dark web monitoring simply does not scale. Thousands of communities produce millions of posts daily in multiple languages with heavy obfuscation. Threat actors maintain multiple identities across platforms. DarkMine was built to close this intelligence gap. So this is about the background and related work. Before diving into our approach, let me position this relative to existing work. Darkbird is excellent at classifying dark web documents, but it doesn't extract fine-grained entities. It can't pull out specific actor names, infrastructure details, or campaign identifiers. SecureBird, Cyberbird handle security advisors well, but weren't trained on unique vocabulary and obfuscation patterns you see in underground forums. Traditional community detection, like Lowian treats all edges equally. It doesn't distinguish between controls infrastructure and mentions a tool which carry every different attribution weight. And classical Hawks processes for crime prediction don't incorporate the natural language processing extracted intent signals we can pull from forum discussions. DarkMine is, to our knowledge, the first framework that unifies all of these capabilities, domain adapted NER with 47 entity types, heterogeneous GNN organization detection, and temporal prediction, validated on over 3.3 million, around 3.3 million records from 15 underground communities. So this is the system architecture of DarkMine. At a high level, a 5-component pipeline. We ingest data from three source types, 2.3 million forum posts, 847,000 marketplace listings, and 156,000 IRC and chat logs. So component 1 handles pre-processing of all this data that we have inputted, the HTML cleanup, the language detection, the normalization, and decoding these emails, of course, and crypto addresses. Component 2 is our domain adapted BERT NER system that extracts 47 entity types with an F1 of 0.87. Component 3 is a heterogeneous graph with over 6,200 nodes and nearly 48,000 edges across 5 relation types. Component 4 applies our heterogeneous graph neural network with type aware attention to detect 312 criminal organizations. And component 5 uses a marked Hawks process for temporal prediction, forecasting attacks 14 days ahead with 72% precision. The key outputs are criminal organization maps at 85, around 85.2 percent precision, infrastructure attribution at 78.4 precision, and attack predictions at 72%. Okay, this is about the data collection and ground truth. Let me talk about our data and ground truth, since this is critical for evaluating any threat intelligence system. We collected data from 15 dark web communities over 18 months from Jan 2024 through June 2025. This includes 7 marketplaces, 5 forums, and 3 chat channels, totaling about 959 gigabytes of raw data in English, Russian, and Chinese. For ground truth, we compiled 94 confirmed threat actors from 3 sources, 47 from FBI and DHS confirmed operations, 31 from incident response engagements, and 16 from established threat intelligence firms like CrowdStrike, Mandiant, Proofpoint. Our NER training data, that is 5,000 posts, were annotated by 3 analysts, each with 5 or more years of cyber threat intelligence experience. Inter-annotator agreement was strong. Fleece cutoff 0.81 for entity boundaries and 0.76 for type classification. Importantly, all data collection was conducted under an IRB reviewed protocol with passive observation only, no account creation, no participation in forums, no purchasing of illegal goods and all. Component 1.2, the domain adapted natural language processing pipeline. Now let me walk through this pipeline in more detail. Phase 1 is domain adaptation. Standard BERT doesn't know dark web slang, code words, or the weird patterns and all. So we continue pre-training BERT large, that's 340 million parameters on our full 2.3 million post corpus using masked language modeling. This teaches the model the unique vocabulary of underground communities. Phase 2 is NER fine-tuning on our 5,000 annotated posts with a CRF output layer. We defined 47 entity types organized into 5 categories. The actors, including individuals, groups, and aliases. Tools, which exploits then their malware. Rats, frameworks, infrastructure, and C2, botnets, proxies, and the targets are organizations, sectors, and regions, and campaigns are operations and code names. The result shows an 11% improvement over non-adapted BERT, which really demonstrates the value of domain-specific pre-training. A critical piece is entity linking. Threat actors maintain multiple pseudonyms across communities. We compute contextual cosine similarity between mentions and merge identities when similarity exceeds our threshold of 0.85. This consolidated around 2,300 pseudonyms into 312 unique identities. The component 3 is heterogeneous graph construction. So that feeds network information that feeds our GNN. We have 5 node types totaling 6,269 nodes, which are again 312 actors, 1247 tools, 3482 infrastructure nodes, and 541 targets, and 687 campaigns. The edges, nearly 48,000 of them represent 5 semantic relation types: mentions, users, commands, targets, and collaborates. Each carries a different attribution weight. For instance, an actor commanding infrastructure is a much stronger signal than simply mentioning a tool. Edge weights combine co-occurrence frequency with temporal decay. Recent interactions are weighted higher. This is important because underground relationships evolve quickly. A collaboration from 6 months ago may no longer be active. This is component 4, which is heterogeneous graph neural networks. So this is where organization detection happens. The key innovation is type-aware message passing. Standard GCN treats all edges equally. But in our domain, the type of relationship matters enormously. Our edge type specific attention mechanism learns, for example, that command infrastructure edges carry more attribution weight than mentioned tools edges. This alone gives us 9.3 F1 improvement over homogeneous. And the process we initialize node embeddings with type-specific features, compute attention weights per edge type using leaky RLU, and aggregate neighbor messages with type-specific weight matrices, and stack 3 layers with residual connections at dimension 256. For organization detection, we extract actor embeddings and apply spectral clustering on the normalized Laplacian. The heuristic determines optimal K, yielding 312 criminal organizations. The results is 85% precision, around 81% recall, and the F1 score is 0.833. And the NMI is 0.78, substantially overperforming all baselines. So this component is about the temporal attack prediction. This is the component 5. It handles temporal attack prediction using marked Hawkes point process. The intuition is straightforward. Successful attacks inspire follow-on campaigns. This is a self-exciting pattern. When one ransom group succeed, copycats and collaborators are more likely to launch their own attacks. The Hawk process naturally captures this cascading behavior. Our conditional intensity function combines a baseline rate, excitation from prior events, and exponentially decay. What makes ours unique is the campaign specific intensity that incorporates natural language processing, extracted intent signals from forum discussions. So when we see chatter increase about a particular target sector or attack method, that feeds directly into our predictions. The numbers 3.2 day, mean timing error 81.3, target sector accuracy, and about 4.2 actionable alerts per week per organization, manageable for SOC teams. We outperform all temporal baselines, including ARIMA, LSTM, Transformer, Hawks, and neural point process. Notably, Transformer Hawks narrows the gap but requires 3.7 times more training time with only marginal gains. So the classical Hawks formulation provides a better accuracy efficiency trade-off. So these are the results on the entity extraction performance. Let me walk you through this more concretely. So our dark miner achieves 0.87 F1 compared to 0.57 for Spacey, 0.7 for Bilstem CRF, 0.76 for non-adapted BRT, and 0.78 for non-adapted Roberta. The key takeaway, domain adaptation matters. The 11-point improvement from standard BERT to dark miner comes entirely from learning dark web vocabulary and obfuscation patterns during continued pre-training. The largest gains are on hard disk categories. Infrastructure entities see a 15% improvement, and campaign entities see 12%. These are exactly the entity types that use the most jargon, which is why domain adaptation has the biggest impact here. The criminal organization detection results are here. For organization detection, our heterogeneous graph neural network achieves 85%, around 85% precision with 0.833 F1, substantially outperforming the Lovian community detection, and 0.60 F1. Node to VEC at 0.69. And the remaining, as you see, 0.77 and 0.74 are for GCN and GAT. Let me highlight the Conti Group case study. So since it provides strong real-world validation, Darkmine detected 47 pseudonyms here linked to Conti ransomware organization, covering 93% of 39 confirmed members from the leaked internal chats. Role assignment is like identifying leaders versus developers versus distributors. It was correct, 81.8% of time, and 3 high degree nodes matched known leadership. On false positives, 46 out of 312 detected
1
organization.
minute left.
Okay. Yeah, so these are more on the numbers. So I'll go on to the operational impact. This is what really matters for practitioners. In this room, we ran a 6-month control deployment study, and 23 organizations received dark mine intelligence briefings with high confidence alerts requiring mandatory defense action. And you can see the results here. I want to be transparent about the limitations. This was a quasi-experimental design with non-randomized assignment. However, baseline security maturity was comparable between the groups, and the large effect size supports the directional finding. This is the ablation study and robustness. 2 important robustness findings. First one is the evasion resistance, and the second is the cascading effect between the components. This ablation is important for understanding system reliability. Okay, I'll quickly go on to the next slide is about the law enforcement deployment. Dark mine has been deployed operationally with 3 federal agencies and 2 international partners. 3 highlights. First, attribution acceleration in one operation. Second is about ransomware interdiction, and the third is about the cross-agency collaboration. Okay, and this is about our future work. First, domain adapted NER, which is achieving 0.87 F1, and BERT that validates the importance of learning dark web vocabulary. Second is about the organization detection with good precision. Third is about the attack prediction, and the fourth is about the production validation. On the bottom line, dark mine shifts threat intelligence from reactive to proactive threat hunting, accelerating investigations from weeks to hours. Yeah, that's it from my side.
Okay, thank you very much. Are there any questions? Okay, I have a question. So regarding the data set, marketplaces, IRCs that you mentioned, how could you collect the resources, the links and the dark webs? How could you find those marketplaces?
So most of them were through the collaboration that we had with different organizations on that part, and also the co-author Sujita also helped me for getting that from her Cornell University data. So that's how we got most of the organizational data.
Yeah, okay, thank you very much. Thanks. Let's move on. Last but not the least, paper ID 484.
Can I go ahead?
Hello, I can hear you.
Can you guys see my screen?
Not yet. Yes, I can see your screen now.
This is Yogesh. I have 2 other partners with me in this paper writing, which is Karthik Pappu and Yogesh Tanvi. They're going to chime in if you guys have any specific questions. So I'm going to go through all the slides here. So today I will be presenting a research-based view of like how DevSecOps work in the ERP space effectively for especially in the release pipelines, the CI/CD pipelines of commercial off-the-shelf ERP products. So in this paper, we are discussing mainly on like the gap that many enterprise team still struggle with, especially in the CI/CD setup in a secure manner. So traditional DevSecOps practices are like good at scanning infrastructure, code, and also the related ancillary dependencies. But they often miss the ERP specific security risk, like which directly impacts the business operations, especially on the commercial side. So this study introduced like a guarded release approach called like ERP release guard. We made it ERP agnostic. Initially, we thought of going with SAP, but then because of the proprietorship, we made it as like ERP release guard as a name for it. And again, like we embedded a security and business controls checks directly into the CI/CD pipeline in our test environment. Instead of taking like a ERP security as a separate audit or governance activity, this research particularly moves through the controls that actually control the release decisions in the CI/CD pipeline. So let me move on to the next one. And again, like the research highlights here are like 94.4% fault detection and 58.3% like regression test reduction, and accuracy is almost one. We use almost 42 controlled runs across like 7 different simulated scenarios, and we use Kubernetes plus Fast API as our release test bed. That's the info setup we did. And this basically also has like a go no go release algorithm, which will take care of a decision based on the test results. Next slide. Okay. In this slide, we are going to explain like why this particular research paper is important. In most organizations, like DevSecOps controls have like matured around cloud native and infrastructure oriented concerns. Teams usually comfortable with like the dependency scanning, static code analysis, like dynamic like testing, and also infrastructure as a code analysis, and even sometimes like the image scanning. These are like important controls, but they do not fully address the ERP specific risk, which are introduced due to the external threats. So ERP environments are fundamentally different because of they manage the industry specific, the finance operations, HR operations, even in like supply chain management companies, they take care of the procurement, supply chain transactions, vendor relations, supply relations. So in this complicated environment, like even a small access control change or a broken business rule can have like immediate impact on their financial operations, data compliance, all those things. So, for example, like if a privilege drift happens in any of the role assignments, like guest access to restricted services or an errors in any restrictive business calculation logics, it can directly impact like the production business operations. There are like recent reports, especially the outage in the production system in the Fortune 500 companies resulted in almost like $1 trillion downtime impact. So, and again, like most of these companies run their day-to-day business on ERPs. And this paper like argues that like this whole technical weakness in the current DevSecOps practices within the industry standard ERPs are like they're performed outside the deployment path just because they have their own like GRC and audit activities. And this leads to risky changes which can introduce uh, defects in the production environment. Yeah. Okay. Here we are like introducing what are our objectives, what are the research questions we considered while designing this paper, and what is the contribution of this whole paper is. Uh, this study is like not just proposing a concept, it's basically testing whether the ERP specific controls can be embedded into release pipelines, and also whether which can improve release assurance in a measurable way. The first question asked like whether the guarded pipeline reduces the security defect leakage compared to a baseline pipeline that does not have a ERP specific controls. In other words, like does this approach actually stop risky releases more effectively? The second question looks at the efficiency part of it. It asks like whether the metadata driven impact analysis can reduce the regression testing effort without allowing more defects to escape into the production. And this is important because the enterprise teams do not want more security if it comes with a huge delivery slowdown. The third question focuses on the decision quality, especially the production release decisions. It asks like whether the normalized risk score gating can produce like reliable go no go release outcomes. So basically here like the paper's contributions combine like theory and practice. It introduced a reusable ERP DevSecOps pattern built along like a lightweight experimental environment using Kubernetes-based fast API ERP. This also injects like faults across multiple scenarios. These are simulated ones, and then measures the detection, leakage, product leakage, accuracy, and regression efficiency. And this basically gives like research both in a technical depth and also the operational relevance for ERP security. Okay. This slide focus on the framework and the release architecture. Here we call our framework as like ERP release guard. The idea is to extend a normal CI/CD release pipeline with ERP over control stages before production deployment. Here the flow starts with the deployment to staging, and then it adds risk-based access control snapshot and drip detection step, RBAC. This basically means like the pipeline captures the current access control state and compares it against approved baseline, which we already credit into our logic. After that, like it performs a guest access probe to validate like whether restricted services are being exposed inappropriately or not. Next comes the impact analysis and test selection. Instead of running all the full regression every time, so the framework select the most irrelevant test bed which are impacted due to the changes introduced into the system. And the selected tests are executed, and then resulting signals are like aggregated to a normalized risk score. And using the risk score and also along with some hard block rules, we can finally make a go-no-go decision in the production deployments. This makes this architecture valuable because it combines like three things into one flow, which is like security validation, function validation, and governance-based release control. And this also like internally controls the like vendor neutral environment, like which means the pattern can be adapted to any of the commercial off-the-shelf products like SAP, Oracle, Workday, or other ERP ecosystems. Yeah. And here we focus on methodology, algorithm, and risk model. So here we define like how the like weighted risk model where overall release risk is calculated using four signals: privilege drift events, and also risk-based access control regression failures, functional test failures, and guest access violations. The whole formula combines like these all the four factors using the weight coefficients. In this paper, like the guest access violations and RBAC issues are given the highest weights, which makes sense because these failures represent directly the security exposure. The functional test failures are also included, but with slight lower weightage. Because like not every function issues is equally severe from a security perspective. And another important design decision here is to use a hard block logic. If the pipeline detects privilege drift or like risk-based access control regression or guest access exposure, the release is automatically marked as no-go, regardless of the total score. So there is a strong governance feature because it reflects a reality of the compliance-driven environments where certain failures are non-negotiable, even though it scores higher in the other weightage categories. The algorithm here follows a logical sequence of like readiness checks, a smoke test, risk-based access control capture, baseline comparison, guest access probing, impact-based test selections, test execution, score computations, and then the final release decision, which is based on all the scores which are capped in the previous steps. From an enterprise perspective, this is very practical model. And again, like this is ERP agnostic, it can be adapted to any commercial ERPs because it creates a very deterministic, explainable and auditable gate so that it's easy to come to a conclusion like whether it's a go, no go based on all these logical weightages. Okay, let's move on to the next one. And here we focus on the data set, testbed, and experimental setup. We built a lightweight Kubernetes-based testbed using fast API microservices, which basically simulate the ERP style components, a gateway, an account service, an HR service, and a database mark. The environment here uses like shared configurable variables to inject like different fault types. So these include like RBAC drift, guest access exposures, calculation and the business rules based defects. So these faults are like modeled at different severity level, creating a structured set of scenarios for comparison. The test suite contains almost like 32 test cases organized into 10 files covering the financial accounts, HR, authorizations, even the cross-module behaviors. And like we worked with sophisticated researchers to figure it out, like how do both the pipelines can compare with each other, and we ensure that we have multiple pipelines to do a logical analysis. So we have like a baseline pipeline and also guarded ERP release guard pipeline just for the comparison purpose. And here, like this whole setup also makes study pretty stronger because the results are based on the repeatable controlled fault injections, and we tested it multiple times before we come back with the result inference. These are the key findings, especially detection rate and test effort reduction. The first major finding is around detection. The base pipeline did not effectively stop the injected faults, while the guarded pipelines achieved like 94.4% detection rate. And this is a strong improvement and shows that additional ERP hour controls materially improves the release protection. The second major result is an efficiency improvement. Here, like using the impact analysis and targeted regression selection, the guarded pipeline had a reduced test effort by an average of like 58.3%. For example, if you had 200 test cases within our core regression suite, we got only like 80 which are really impacted. Remaining 120 we could have saved in terms of effort and uh, time. And this is very important because it shows paper is not arguing for more controls through a brute force, but instead it's focusing how to improve both the release assurance and test efficiency at the same time. And there's some additional runtime overhead, but the paper indicates that overhead is relatively small in absolute terms. And when compared to the benefit of blocking risky ERP releases, that additional time is operationally acceptable. So the takeaway from this slide is that framework improved both quality and security outcomes while still maintaining a practical pipeline flow. Okay. And here we focus on risk score gate accuracy and the decision reliability. So in the enterprise DevSecOps setup, it's not good enough to detect only problems via the release changes. So we need to have a sophisticated quality gate that also has a reliable delivery team which can keep observing the releases happening in the system. Provided if it generates too many false alarms, people will eventually try to bypass it. So this paper particularly reports a precision of almost 1.00, which means the pipeline did not falsely reject clean releases. That is also a very strong result because it shows a gate is not overreacting. At the same time, the recall value is also high. So meaning the pipeline caught most faults successfully in the initial quality gate itself. And here the graph shows a clean runs clustered at zero risk, while fault runs produce significantly higher scores. That separation is important because it demonstrates that scoring models has meaningful discrimination power. There was also one escape case, and the paper attributes to a transient timing issue related to a prod restart delay during our risk-based access control snapshot collection. But overall, this slide supports a very important conclusion. The release gate is both strict and dependable, which is exactly what enterprise teams need, which can let them release the code to production with ease and confidence. Okay. Here we are just doing a kind of a comparison to enterprise enterprise ERP or SAP DevSecOps, the relevance to it. Here the pattern described in the paper, it can be mapped directly into real ERP release engineering workflows. For example, role matrix that can SAP or Oracle landscapes can be validated using a snapshot and differential style checks, similar to RBAC control in this paper. Guest access problem can be translated into API exposure checks, integration endpoint validations, or service access verifications. And the risk score gate can be aligned with transport approvals, release readiness reviews, or chain governance checkpoints. The broader value here is that ERP security is no longer needs to be a separate audit exercise, which happens after the deployment. Instead, it can become part of the release evidence chain. So there is a shift left approach here. That means every release carries auditable proof of access validations, targeted functional assurance, and also release time compliance. SRP, basically SAP and ERP transformation programs, this is especially relevant because organizations are trying to modernize the release processes without weakening the compliance postures. And most of these Fortune 500 companies, they're all like publicly listed, so they have to abide by the SOX rules. So this paper shows like a clear path towards like continuous compliance, release level governance, and stronger integration between the quality engineering, security, and DevOps. So the practical takeaway is that like the research happened here is not just academically interesting, but it directly useful for enterprise CI/CD modernization. Okay. Here we quickly go through some of the limitations, future scope, and strategic conclusions. This paper is yeah. This paper is careful to acknowledge that like the prototype environment is simplified. It uses fast API for simulations. And instead of using a full production ERP landscape, we've only focused on industry standard risk, which we simulated using fast API. And the RBAC model used here is limited because we did it in a test environment, but it can be expanded in a practical, bigger landscapes. And the scoring weights were defined through expert judgment rather than tuned with the live historical data. And we also referred multiple research happened in this particular area. Regarding limitations, here, like we do not reduce the paper's value uh, by focusing on limitation. In fact, like they help frame the next stage of the research. And the future scope includes extending the model to segregation of duties, like SOD scenarios, which are more industry standard, and we can consider all kind of combinations which are specifically ERP. We can also do broader cross-module workflows, dynamic weight tuning based on the production telemetry, which is specific to a specific company, and also testing at a larger ERP scale. To close with, I would position this paper as a very strong step towards enterprise-grade ERP DevSecOps, where release pipelines do more than deploy code, and it can actually actively enforce business-critical security controls before the change reaches production. Okay, I'm ready to take questions.
Okay, thank you very much. Are there any questions? Okay, just a quick question regarding the risk weights. How did you come up with those numbers? Just randomly, or did you have a baseline for that, reference for that?
We had like 7 core fault injection scenarios, and we did a kind of specific weighting for those faults. And we introduced with almost like 32 different combinations of this risk into the system to figure out like whether our algorithm captures it in a proper manner and give us the right risk score. So even one of my research associate, Karthik Papu, is a PhD student in South Dakota University. So he came up with the complete risk-based like a matrix, which was referred from an industry standard, which is already communicated in IEEE papers or some other papers. So.
Okay, thank you very much. I appreciate it. Okay, let me conclude this session by thank you all for attending this session. I enjoyed your presentations. We had very good papers here. Hope you have a great rest of your day and hope you have a great weekend. Bye-bye.
Thank you, man.
Thanks.
Bye-bye.
Thank you. Yeah, bye.
Thank you. Bye.